All right, so we're gonna finish this up partly. We're gonna go 28 through 36, and hopefully I can do them all. Yeah, we should be all right. So without further ado, let's get started. Number 28, related rate problem, of course. Okay. Person stands 30 feet from point P, watches a balloon rise vertically from a point as shown as the figure below. Okay. The balloon is rising at a constant rate of 2 feet per second. Anytime I see that, I just make a note for myself. A rate is a derivative, so you definitely want to label that as best you can. And related rate problems are always with respect to t time, so it's a rate of change in radians per second of the angle theta at the instant when the balloon is 40 feet. Person stands 30 feet from point P, watches a balloon rise vertically from the point as shown in the figure below. Balloon is rising at a constant rate of 2 feet per second at what is the rate of change in radians per second, the angle, instant when the balloon is 40 feet above point, okay, I missed that one, above point P. So they're telling us they want to freeze time when that is 40. All right. So if we look at theta and we look at the information given, we know that this is the opposite side and this is the adjacent side. So that means we need to focus on the tangent function. And tangent will be opposite y over adjacent x. Okay. And when we do this, we're taking the derivative of everything with respect to time. All right. But what, before we get started, do we know about the person to point P? It's 30. Is it always 30? And the answer is yes. This is always 30. This is a constant in our problem. The person is not moving closer or farther away from point P. The balloon is moving farther away from point P, but the person stays exactly where they are. So what that happens in this problem is that this x is no longer an x and gets replaced with a 30. That helps us out immensely when trying to do the derivative of this question, which is eventually our next step in the process, is we want to be able to take the derivative. But in order to do so, we would have had to do the quotient rule over here, which is doable, but we don't know what dx dt is. We do know what dy dt is, and that's going to come into play later. But dx dt, that's not coming into play. So that would have given us a little bit of grief. Okay? So let's continue on. So looking at this problem, let's take the derivative with respect to t. So let's do the left-hand side first. So the derivative of tangent is secant squared theta times, there's a nested function here, d theta dt. Now, if it would have been tangent of t, then we would add dt over dt and problem solved. But with related rate problems, we have to do d theta dt, and we'll actually have dy dt over here. Because the derivative of y is just a 1, but you still have to take the derivative with respect to t. So that leads us to the dy dt. Now, the question asked us, what is the rate of change in radians of the angle? So we're looking for d theta dt. This is what we are solving for. So in that case, we can start to isolate the dy or d theta dt. Now, secant squared cos can't be bros, so cosecant and cosine can't be bros, so secant means that is going to be 1 over cosine squared theta times d theta dt equals 1/30 times dy dt, which we know is 2. So now we just need to know what cosine squared theta is. Well, we have a triangle and we have an adjacent side. We can calculate the hypotenuse with a squared plus b squared equals c squared. So that will give us 30 squared plus 40 squared equals 50 squared, right? 3, 4, 5, Pythagorean triple. I don't know. Let's see. Let's find out. Would it be 2 zeros? 30 times 30 would give us a 0 and a 0. Yeah, I think so. All right, and that's going to lead us to c squared, which will be 2500, which is 50 squared. Okay, I like it. All right, so this becomes 3, 4, 5, or 30, 40, 50. Pythagorean triple. So now, when we're looking for the cosine of theta, the cosine of theta equals adjacent over hypotenuse. So 1 over cosine theta just means that we're going to flip the 50 and the 30. So then this becomes 50 over 30 times d theta dt equals 2 over 30. Then we can multiply by the reciprocal, 30 over 50, and then 30 over 50, which the 30s cancel out. I'm left with 2 over 50, d theta dt, which should simplify to 1 over 25. Okay, what did I screw up? Must have been my Pythagorean triple. What's my problem? 30 times 30 is 900. 40 times 40, 1600 plus 900 equals 2500, which would be 50 times 50, right? Yeah, that was right. No, that's not my problem. Oh, man. Okay. I see it. I see it. What is 50 over 30? Well, that's 1 over cosine. But what do we have? Technically, we have 2 of them. Technically, we have 2 of them. So, we need to backtrack a little bit. Which, if you show all your work, it's not too bad of a backtrack. It really isn't. So we only screwed up, really, for the 30 over 50. And then this 30 cancels with one of them, so we're left with 60 over 50 squared, which is 2500. Zeros cancel, and I'm left with 6 over 250, which we could take a 2 out of them. It's 125, cancel out the 2's, and then 3 over 125. Boom. Solution. Boom. So sometimes going through and doing this kind, sorry, let's get all that out of the way. Yeah, I mean, they literally go through the same process we do, sort of. Oh, they just simplified it to 5 over 3. Meh. Shmeh. I don't know. I don't hate what we did. 50 over 30 isn't terrible. I don't know. Oh, whatever. Good enough for me. What one am I skipping? 30. Okay, so I can do this one. All right, how many vertical asymptotes does your graph have? Okay, so when we're looking for asymptotes versus holes, what you're going to notice, or what you're going to find out, is that if something cancels on the top and bottom, this is a hole. Where if you just have 1 over this, this is an asymptote. So that's the difference between the two. So we have to figure out, is x minus 2 going to cancel with something? X minus 2 over x squared minus 4 and x squared plus 4. And then we can keep going into x minus 2, x plus 2, and then we still have an x squared plus 4. And then this is x minus 2. So then the x minus 2's cancel out, and I'm left with 1 over x plus 2 and x squared plus 4. And if we take those, and set them equal to 0, we're going to find that this x value is at -2, which makes that undefined. And can we square anything and add 4 to it and get 0? And the question is not in the real world. We can do imaginaries. So really, this only has one asymptote, and it is at x equals -2. The one at +2 is just a hole, and there is none here, which means that when you have like a max or a min, what's happening is something's happening above the x-axis or below, or just somewhere else. I guess I can't guarantee that. I think that's how that works. But there's something else going on where those zeros are. They're just not crossing. Well, maybe it's just a glitch in the matrix where you got... No, now that I stuck my foot in my mouth, let's Desmos that and find out. Okay, so what are we looking for? F x equals x minus 2 over x to the 4th minus 16. Oops, 16. So we get +2 is undefined, so there's our hole. Here's our asymptote. But when we do x squared, let's see, does zooming out do anything for us? No, it doesn't even show any blip or anything in the radar. I mean, it could be one of those where it U's up and then we get this on the backside. That could possibly happen if it's something where we can get another asymptote. But in this case, no, we just get that. So this is 1. Final answer, boom. And for x cannot equal 2, the graph has only one vertical asymptote. X equals -2. The graph has a removable discontinuity. Yeah, so once again, they don't even say anything about that. Ooh, summation problem. I'm curious, for what value b does the integral 1 to b x squared equal the summation? I feel like this is a BC question, or what are they? I don't know what they're, unless they're looking at integration of the summation of how we looked at those. But wow, yeah. Yeah, I don't know. This one definitely sparked my interest. I should probably look and see like what assessment it's on. Integration and accumulation of change. I figured that. The fundamental theorem of calculus, though. I don't know. I think that's a stretch. I mean, maybe I'm wrong. Delta x is 2 over n. Yeah, I don't know. I think I would have had a tough time teaching that one for reals. All right, first rule graphs, no graph we're looking at. So we are looking at increasing, decreasing, max and mins. And I tell my students that whenever I do this, the first thing I do, if I know it's a first derivative graph, plus, minus, plus. Then if we go positive to negative, that's a max. If we go negative to positive, that's a min. Okay. So I'm already labeling those things on my graph just to help me out. I just want to make sure that I look at that and pay attention to that, and I know that's what this is talking about, and that's what this is talking about. All right. So let f be a continuous function over the closed interval from 0 to 5, all right? If the graph f prime, the derivative of f is shown above, which of the following intervals is increasing? So we know from 0 to 2 is increasing, because all of this is above the x-axis. From 4 to 5 is increasing. And there's some little glitch here that's happening that might come into play. So let's see. So we have from 0 to 1, zero to 2, and 4 to 5. Don't overthink this, unless I feel like you're just going to overthink this. We're looking at the first derivative. What's increasing is what's above the x-axis. What's above the x-axis from 0 to 2 and from 4 to 5. I don't know why. I can't. I'm going with it. Final answer. Okay. Jeez. All right. See, they just try and throw all that stuff. I'm like, what? No, it's okay. Moving on. Sometimes. The height of an object at time greater than 1 is given by this. What is the velocity? Ooh, okay, so the height. So we're looking at h of t. So we want h prime of t because that is velocity. Because we have position, velocity, or we could have done acceleration with the second derivative. But we don't need that, so I don't want to put it in case it gets in our way. Only looking at h prime. So what is h of t? H of t is t squared minus 16t, or as I like to write it, 16t to the negative 1 plus 15. And if we are doing the derivative, and I'm gonna throw this over the side, t equals 3, because we do want to know the velocity of the object at t equals 3. So taking the derivative 2t, because the 2 goes out in front, and then we go down by 1. This one is going to be a positive 16t, but then we're going to go down another one, so it's going from negative 1 to negative 2, and then this one falls off. So what we have for a velocity is 2t plus 16 divided by t squared. And we want to know what the velocity is when t equals 3. So we're going to plug 3 in. That's going to give us 6, and that's going to give us 16 over 9. And 16 over 9 is going to be 1 point something, 778 probably, because the only answer that's close to 6 plus 1.778 is going to be B. Oh, what? How did you do that? Well, think about it. 9 times 2 is 18, so this has to be a 1, and 6 plus 1 is going to get us one of these solutions, right? So then what's the decimal on it? 0.778. Okay, because remember, these are our choices, so, you know, use what you have. Calculator or no calculator. So a lot of these, whether they are calculator or non-calculator questions, usually can be done without a calculator altogether. Oh, look at that. Oh, okay. So it does kind of tell you if it's a calculator or not. Okay. Let's go on to 33. How we doing? Okay. The function g is differentiable and satisfies when g is -1 equals 4 and g prime at -1 equals 2. What is the approximation of g at -1.2 using the linear tangent to the graph of g at x equals 1? So what we are looking for, this is a line of tangency. So we need y minus y1 equals dy over dx times x minus x1. So we have an ordered pair. Our x comma y is here. We know our dy over dx, that's going to come from there. So when we plug this in, we're going to get y minus 4 equals 2, and then x minus a -1. So y minus 4 equals 2x plus 2. Add 4 to both sides, and I get a final answer of y equals 2x plus 6. And what they want us to do is find g at -1.2. So what we're going to do is we're going to do 2 times -1.2 plus 6, and we are going to get -2.4 plus 6. 6 minus 2 is 4, but minus another, that's 3.8 or 3.6. So we're at a crossroads here. So if we do 6.0 minus 2.4, borrow that, drop that, and then we're going to do 10 minus 4, which is 6, and then do 3. So we get 3.6. Oh, you are more than welcome to jump in Discord. Bummer somebody jumped out. But please stay in. If you have questions, if you have different questions, by all means, don't feel like you can't come in here. So, that gets us to 3.6, which is letter A. Boom. And essentially what they did with theirs, you know, created it. They used a weird looking equation, but it's really the point slope formula. They just moved this over. That's an ugly way to look, but whatever. They did what we did. That's all you need to know. Okay, 34. Tara's heart rate during a workout is modeled by a differential function h, where h of t is measured in beats per minute and t is measured in minutes at the start of the workout. Which of the following expression gives Tara's average heart rate? Okay, so this is average. So we start at 30, we go to 60. Okay with that. H of t is measured in beats per minute. So why would I do that? Well, what do we want? We want the following expression to give Tara's average heart rate. So what we want is the change in y over the change in x is what we're thinking of, or how you should be thinking about this. The change in x is really the change in t. So what we are looking for is the change in the heart rate over the change in time. Okay, so the change in time is easy to do. We can just do 60 minus 30. That's going to be the 1/30th. So that's where you start to get this idea, because we're over a 30-second time frame. Boom and boom. So now we're here. So what we need to do is when we take the integral we want to get the change in heart rate. So we would like to do a y2 minus y1 because we did a, I guess, let's be proper about this, t2 minus a t1. This is the average, this is your rate of change. This is your average value theorem, whatever you want to call it, mean value theorem. So we're going to get 30. But what is going to get us y2? Well, that's going to be h of 60 minus h of 30. That's what we want to have up here. And the only way to get that is if we are going to integrate, we don't want to integrate h of t because that's what we actually want to plug into our formula. So what we want to do is integrate h prime of t so that when we go up to the next level, we will be at h of t, and then we can plug in 60 and 30 and get h of 60 minus h of 30, which is what we're looking for. That's our slope formula. That's the average rate of change. Okay, so that's where we start to collect our thoughts and get letter C as our answer. What? No way. What is that? That's interesting. What did I screw up? Wow, I thought it was good. The average value of the function f over the interval from a to b is 1, b minus a, yeah. And then Tara's average heart rate from that. The average value of the function h over the interval from 30 to 60 would therefore be the expression No, where h of t is measured in beats per minute. Let's start the workout. Oh, okay. All right. Sure. If we look at it from a ratio standpoint, okay, this is probably a better way to think about it. So I did make a mistake. When we want this, we want which of the following expression gives Tara's average heart rate? Well, an average heart rate Hey, disclaimer, I never said I was the best. I just trying to help my students out, and I'm not doing a very good job right now. All right, average heart rate. We want, when we're doing an average heart rate, we want beats per minute, correct? That's what an average would be. We don't want beats per minute. That's not going to help us out. So what happens when we integrate h of t dt is we get back to, I don't know, we'll call it big H. And that's just going to be beats. Those are our beats during whatever. These are our beats, our total beats. So when we do this, what we're going to do is we're going to do the change in beats over the change in time. And what is that going to ultimately give us? Beats per minute. So when we do integrate this, we do want to integrate h of t to get us back. What I was saying was when we do this and we integrate, this gets us back to h of t, which is beats per minute, which is what goes on top, but then we have it over time. So beats per minute over minutes. See how this screws us up? And that gets us beats per minute squared, which is not what we want. We just want beats per minute because we're looking for the average heart rate. Okay, so I did screw that up, and I apologize for that, but it is not h prime of t, it is h of t. Prime of t missed is where my brain went. So h of t goes to h, which is just beats, total beats, and then our change in time is what goes on the bottom for our slope, which is why B is the correct answer, not C. Oh, man, that's a toughie. I get screwed up. My bad. But it does make sense when I think about it in the contextual answer and go back and go, oh yeah, that's where I did make a mistake. So, shame on me. All right, let g be the function with the first derivative g prime here, and 8x is greater than 0. If g of 2 equals 7, what is the value? Oh, here we go. So back to our tangency problem. So we want to create an equation with a tangency and then figure out what it is for this value. This is a very popular problem. So our dy dx is really g prime, and what we're looking for is g prime at 2, because that's the point, that's the ordered pair we have. Because remember, if you're doing this, you want to make sure you're at that point. So we have 2 cubed plus 2, and that's 8 plus 2, which is square root of 10. Yes, you said it. So this dy dx becomes the square root of 10. And then we have x minus x1, which is 2, and y1, which is negative 7. So we get y plus 7 equals the square root of 10, x minus 2. We will subtract 7 from both sides. And here's a good example of what equation they were trying to show you. Because distributing the square root of 10 doesn't really help a whole lot. All right, so what they want is they want this at a value of 5. So what we're going to do is we're going to take that, do 5, take away 2, minus 7. So this would be 3 times the square root of 10. And then we're going to subtract 7 from it. So when you think about the square root of 10, and this is what I try and tell students of mine, is like, think about your perfect squares. You have the square root of 9 and you have square root of 16. Well, the square root of 9 is 3, and the square root of 16 is 4. So where does the square root of 10 fall in? Is it closer to 9 or it's closer? So this would be like, I don't know, probably like 3.1, 3.2. So if we do 3 times 3, we're going to get 9. Ooh, interesting. Oh, it's cubed. Oh. Yeah, 2 times 2 is 4, times 2 is 8, plus 2. Okay, I don't see what's wrong with that. 8 plus 2 is 10. Then we did x is 2, y is negative 7. I don't see a problem there. We're going to subtract 7 from both sides. Don't see a problem there. Then we did 5, and that's going to give us 3 squared root of 10 minus 7. I don't know if I see anything wrong with my math, but I don't think I'm seeing the answer that I need. Okay, so we're going to do 10, and we're going to take the square root of that. And, yeah, no. So then that would be times 3, which is 9.4 minus 7. It's going to be 2.4. But that answer definitely is not up there. Let g be the function. And by any means, feel free to chime in. Oh, okay. This isn't a slope of tendency problem. Oh, all right. Well, that would explain it. They aren't looking for that. They're looking for this. Interesting. Okay, so let's backtrack a little bit. We have x cubed plus x to the 1/2 power. Squared plus 1 to the 1/2 power. With the first derivative. Okay, you are not going to be able to use this without a calculator. This is where g of 5 minus g of 2, therefore 5 equals g of 2 plus 2 to 5. Wow. Evaluate the definite integral is done with the calculator. Okay. All right, so let's see if we can make some sense of this. We want to go and integrate g prime. Well, I said that, but what are we thinking? If g, what is the value of g5? They went from this standpoint. G of 5 minus G of 2 equals the integral from 2 to 5 of G prime of x dx. Okay. So what they're saying is that if I need G of 5, I can move this over to the other side and integrate from 2 to 5 G prime of x dx, but then I can add G of 2 onto it to get my solution. Oh man, that is clever. That is how you do it. And that makes a lot of sense. I don't think I would have came up with that. Weeding it out, I don't know. It's above my pay grade, but it makes sense. Makes complete sense. And remember, this test is for weeding people. It's not to get 100% on. There's going to be questions like this that you're going to have to manipulate what you think. And you saw me, I started with a line of tangency. I wonder if that's what I put here too. Break up the integrate. No, so my hint was, I don't know if my hint really would help, but curious. Okay. Well, it makes sense. I mean, if we integrate g prime, we're going to go to g, and if we go from 2 to 5, we're going to do g of 5 minus g of 2. And if we want what g of 5 actually equals, we need to move the g of 2 to the other side. So we have this integration, which we can do. We have a function. We've got two numbers we're going to plug into it. We can do that on a calculator very easily. And we already know what g of 2 is. It's -7. So that's where we're getting -7 plus this integration equals 13.899. And thankfully, they showed you, like, when I did this square root of 10, x minus whatever it was, 2 minus 7. Thankfully, like, when you plug x in, like 5 in, there was no answer here. So I knew this process was wrong. So I had to start thinking of a different process. Like that was not what the question was looking for. So thankfully AP, I think, does that a little bit to you to help you out. But wow, that one was tough. That was no joke. All right, 36. Let's clear that off. And f is a function that has removable discontinuity at x equals 3. Which of the following could be a graph? Now, when they say removable discontinuity, did they say it was a jump discontinuity? AKA, AKB, or just a removable discontinuity? What happens with D? That's an asymptote. That's not even a removable discontinuity. I mean, for me, there was only one clear-cut winner, but be careful because it says check all that apply, but I only see one winner. But I've been known to be wrong before. I'm not in this case, though. So that is a removable discontinuity. All right, so that gets us through 28 through 36. On Wednesday, we will finish up the last of this. Look at number 44. Increasing and concavity connect them. I didn't get this until I looked at the solution. Yeah, break up the integrant. This one I might even just put definition of integration. I didn't get this until I looked at the solution. So as I learn things, I fix it and correct it for my students for years to come. Like I said, I'm not the be-all, end-all. I just work through these things, and you learn as you go sometimes. It was clever. It was clever. I still guess need to brush up on my summation knowledge, though. What was this one? This was, where was it? Here. I don't know. Yeah. A right Riemann sum. I guess. Man, that one's tricky for me. So yeah. 37 through 45 we will do on Wednesday. Pause, do whatever you need to do, go through the problems, do the best you can. If you are not a member, please feel free to jump in Discord. This is our Discord channel, and jump in this channel. Somebody jumped in, jumped out, but it's okay. It's easy for you to ask questions if you're in this channel, watching the stream as opposed to Twitch. You gotta type in your questions. Excuse me. You have to type in your questions, and then I have to notice them, and it doesn't make a noise. Sometimes I try and put alerts on, but let's see. Chat field, no. Yeah, I don't know. So don't be afraid to come in here or post questions in the questions tab. Once again, schedules Monday and Wednesday from 8 to 9. Jump in for free consultations. And that will wrap us up. So have a great night and have a blessed day.